Welcome to the presentation of our online course, Introduction to Microbial Fermentation Technology and Engineering. Through our online courses series, you learn the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and animal cell cultures processes. For more details, visit us at bioprocessengineeringonline.com. Fermentation processes are extensively used across the food, chemical, pharmaceutical, and environmental industries. These processes involve a series of operations that convert raw materials into valuable bioproducts. At the heart of fermentation processes is a biotransformation step, in which microbial cells are employed to carry out the desired conversion. In fermentation processes, microbial cells function as cellular factories, harnessing their complex metabolic networks to grow and produce a wide range of valuable compounds. Through metabolic engineering, microbial cells can be tailored to synthesize recombinant proteins and novel metabolites. In addition, they play a key role in environmental applications by degrading and removing pollutants. For bioprocess engineers, a major challenge lies in designing and scaling up fermentation processes that are both efficient and cost-effective. A key focus is the scale-up and optimization of the core fermentation step, beginning with initial cell propagation in laboratory Erlenmeyer flasks and advancing to large-scale fermentors, capable of producing kilograms to tons of product. This introductory course in microbial fermentation technology and engineering is intended for students and professionals who are new to bioprocess engineering and/or its applications in microbial fermentation. Participants will first become acquainted with the fermentation technologies commonly used in industry. The course also provides a foundational understanding of how bioprocess engineering supports the simulation, scale-up, and optimization of fermentation processes for industrial applications. The course is organized into 3 sessions, covering fermentation technology and cost, fermentation kinetics and simulation, and microbial fermenters' optimal operation. The sessions can be taken independently. Session 1 begins with an overview of industrial fermentation technologies. It introduces the main types of microorganisms, bacteria, yeasts, and fungi used to produce a wide range of products, including small molecules such as organic acids, amino acids, alcohols, and antibiotics, macromolecules including enzymes, therapeutic proteins, polysaccharides, and DNA, cells such as starter cultures, probiotics, and those involved in the production of fermented foods like beer and wine. In addition to product manufacturing, microbial fermentations are also employed in environmental applications, such as wastewater and waste treatments. The session explores the composition of fermentation media, highlighting how it is formulated to meet the specific nutritional requirements of microbial cells. Fermentation media, whether complex or chemically defined, are designed to supply essential components such as carbon sources, nitrogen sources, minerals and trace elements, salts and buffering agents, vitamins and growth factors. The session also reviews the types of fermenters used in industrial applications, both for anaerobic and aerobic processes. The most commonly used systems are stirred tank fermenters, which can range in volume up to several thousand cubic meters. In addition, the session introduces alternative, less commonly used technologies, such as membrane fermenters with cell retention systems, and fixed-bed reactors containing immobilized cells. In the second part, Session 1 introduces the economics of fermentation processes. It presents the methodology used to evaluate production costs, considering key cost contributors such as raw materials, equipment, energy, and labor. Understanding cost evaluation is essential. It is a critical prerequisite for optimizing fermentation processes. Fermentation production costs can vary widely, ranging from just a few euros to several million euros per kilogram of bioproduct, depending on the product and process. The next two sessions introduce the engineering principles of microbial fermenters. Bioprocess engineering is a scientific discipline that offers a conceptual and methodological framework for understanding, simulating, scaling up, and optimizing microbial bioreactors. Its goal is to ensure the most efficient and productive use of microbial cells in biomanufacturing processes. Session 2 focuses on the kinetics and simulation of microbial fermentations. It introduces the bioprocess engineering approach used to determine and analyze the kinetic parameters of microbial systems. Building on these insights, the session covers the development of knowledge-driven simulation models for fermenters, enabling a deeper understanding and more effective control of fermentation processes. Session 2 begins with a review of the key kinetic behaviors in microbial processes. These include substrate consumption, mainly sugar carbon source and oxygen, cell growth and death, as well as the production of metabolites and recombinant proteins. The session also explores metabolic shifts commonly observed in industrial fermentations, transitions in cellular behavior that can significantly impact productivity and yield. The session then highlights the key biochemical and physical phenomena that govern fermentation kinetics and influence the microbial rates: cellular conversion reaction, oxygen and carbon dioxide solubility and mass transfer, fluid flow, and possibly heat transfer within fermenter. Session 2 finally introduces the knowledge-driven methodology used by bioprocess engineers to develop simulation models of fermenters. This approach is based on the balances thermodynamics-kinetics triangle, which integrates mass balance equations with the thermodynamic and kinetic laws governing the key phenomena identified in the fermentation process. These simulation models serve as digital twins of real fermenters. They enable efficient virtual experimentation, digital scale-up, and process optimization, greatly reducing the need for costly and time-consuming physical trials. Session 3, Optimal Operation of Fermenters, introduces the core principles of optimizing bioreactor performance, with a focus on aligning operational strategies with the specific kinetics of the cellular biotransformation. The session outlines the rationale behind selecting the most appropriate mode of operation, batch, fed batch, or continuous fermentation, when scaling up a process for industrial production. Session 3 begins with a focus on batch fermentations. It reviews the fundamental principles and kinetics of batch processes, highlighting both their advantages and limitations, particularly the challenges associated with high substrate concentrations, which can lead to the accumulation of inhibitory metabolites. Batch fermentation is widely used for anaerobic processes that produce metabolites, such as organic acids, alcohols, or solvents. In this session, you will explore how key operational variables, such as initial substrates concentrations and the timing of product induction, affect the kinetics and overall performance of batch fermentations. The session then introduces the principles and kinetics of fed batch fermentations, which are designed to maintain key substrate concentrations at low controlled levels throughout the process. Fed batch strategies offer several key advantages. They reduce the formation of undesirable byproducts associated with rapid cell growth. They enhance the production of non-growth associated metabolites. As a result, fed batch fermentation is widely used for producing active cells and non-growth associated products, such as secondary metabolites or recombinant proteins. You will examine how key operational variables, such as steady-state substrate levels, feed concentrations, and the timing of product induction, influence the kinetics and overall performance of fed batch processes. Session 3 finally introduces the principles and kinetics of continuous fermentations, which are designed to operate fermentations under prolonged steady-state conditions. Continuous strategies offer several key advantages. They reduce the downtimes between consecutive fermentations and can operate under low substrates concentrations. As a result, continuous fermentations are mainly used for producing active cells and for water and waste treatments. In this session, you will examine how key operational variables, such as medium flow rate and substrates feeding concentrations, influence the kinetics and overall performance of continuous processes. Throughout the session, the simulation of fermentation in different modes will be illustrated using three common types of microbial fermentations: anaerobic production of a growth-associated metabolite, namely ethanol; aerobic production of microbial biomass, in this case yeast; production of a non-growth associated metabolite, namely an amino acid. These case studies will provide practical insights into the kinetics and operation of different fermentation processes. The course resources include recorded slideshow presentations covering microbial cells kinetics, fermentation simulation models, oxygen transfer and consumption in microbial fermentations, microbial fermentors operation and optimization. In the 3 sessions, you will use spreadsheet templates to analyze fermentation kinetics, simulate fermentations in their batch, continuous and fed batch fermentation modes, and optimize fermenters operation for maximal productivity. You have the flexibility to tailor this online course to your individual pace. Plan and structure the course according to your own schedule. Additionally, coordinate the interactions with your tutor through video meetings. For further information on the course, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com.